Então, thank you very much, Professor Martinelli, for accepting our invitation. Professor Antônio Eduardo Martinelli has been working in materials and metallurgical engineering, especially on ceramics, metal ceramics interfaces, cements, and composites. Professor Martinelli is currently a professor at the Department of Materials Engineering of the Federal University of Rio Grande do Norte, Scientific Director of SBPMAT, and Coordinator of the Materials Area of CAPES. I would invite Professor Martinelli to start his presentation on solvothermal synthesis of ceramic powders under pressure. This presentation will be presented simultaneously on Google Meet and the YouTube platforms. Thank you very much, Professor Martinelli.
Thank you, Professor Edgar, and all my friends and colleagues from UFAN. It's a pleasure to be here with you. Congratulations on the organization of this conference, Molecular Physics, and on the use of the virtual platforms to make it easier for people from all around the world to participate. So congratulations for the initiative of the organization of this conference. And again, thank you very much for the invitation. It's a pleasure to be here, and it's a pleasure to meet so many good friends. I will just close my my camera for this presentation during the presentation, because I'll be looking at the second monitor here, so it's more comfortable not to show you my side view all the time. So we are here to talk about solvothermal synthesis of ceramic powders under pressure. This work has been developed at Universidade Federal do Rio Grande do Norte, UFRN, specifically students with the participation, the collaboration of postgraduate students of the Material Science and Engineering program, and also with the collaboration of fellow institutions such as the Universidade Federal do Espírito Santo, Universidade Federal de Santa Catarina, and funded partially by ArcelorMittal and by the National Oil and Natural Gas Agency. We have a PRH program here, which is specifically for students of undergraduate and graduate materials courses. Okay, so this is a little bit of our research group. We have new acquisitions here, such as Camila, Eduardo, Will, and we are now all working on the synthesis of powders and nanofibers also, and on the use of these materials, especially on metal reinforced composites. Part of the equipment that we use, which is not the main reactor that will be discussed during the presentation, a little bit along the way this morning. Here we have a hybrid plasma resistance reactor, which is used for the preparation of the composites once we have the reinforcement materials. We also work on the synthesis of nanofibers in collaboration with Professor Rogerson, here from the Textile Engineering program. What you see here on the right side, the lower right side, is the preparation of fibers by nanofibers by solution blow spinning. This kind of fiber that we see specifically on this short video is PVA chitosan fibers. This is just the beginning. We're just showing you some extra material before we go to the presentation itself, which we do now. So, talking about synthesis, the solvothermal synthesis is a wet method to produce powders inspired on the natural formation of rocks and ores from the action of a solvent at high pressure and high temperature on precursor powders. So we are here again imitating nature. This synthesis route stands out for its ease of handling of the process parameters, enabling superior control of the resulting materials, characteristics, and properties in terms of composition, crystal structure, morphology, and most important, at a reasonable time. The word hydrothermal is a geological term, was first used by British geologist Sir Roderick Murchison to describe the effects of high temperature and high pressure water on the Earth's crust in the formation of rocks and minerals. The first hydrothermal synthesis was carried out to produce quartz crystals by German naturalist Carl Emil von Schoefelt. I don't know if my pronunciation is correct, using a piece of equipment designed by the French physicist Denis Papin, which is known as the Papin's steam digester, which looks very much like a pressure cooker. So here we have a picture of the original equipment comparing to the modern cookers that we use in the kitchen. And this was developed in between the late 17th century. And this is the French physicist Denis Papin. Okay, so the solvothermal method was, this is a mid-summary of what we have been discussed. What has been discussed. So the solvothermal method has been used by geologists for the reproduction of the natural conditions in the synthesis of synthetic materials and the treatment of natural compounds. And its first applications were based on mineral processing in the 19th century, and then the growth of quartz single crystals in 1946 because of their piezoelectric conditions, and after that in the production of zeolites, which are molecular sieves. In Brazil has a large reserve of quartz, and during the World War, the Second World War, there was an export embargo which limited the export of quartz crystals to the US, to the Allies, because it's a strategic material for telecommunications, which forced other countries such as Japan and Germany and so on to be the pioneer in powder processing, and from the 80s on, novel applications of the method. So the definition of solvothermal synthesis is any homogeneous or heterogeneous chemical reaction in the presence of a solvent at a temperature above ambient and an absolute pressure greater than 1 atmosphere in a closed system. This definition was brought by Barapa and co-workers in 2013. The term hydrothermal, the word hydrothermal, is commonly used to replace solvothermal, even when the solvents are different than water, such as alcohol, benzene, ethylene glycol, and so on. So, in general terms, the solvothermal synthesis starts with a solution containing precursors based on the elements that form the target material, including nitrates, chlorides, sulfides, alkoxides, among others. In a liquid environment, a solvent, such as water, alcohol, or hydrocarbons, and controlled pH. Solution is transferred. Additives may be used to assist in the process. The solution is transferred to a synthesis reactor, which is properly sealed and heated. As the temperature increases, there's also an increase in pressure that is inherent to the thermophysical properties of the solution. So the synthesis mechanism, the main synthesis mechanisms involved in the solvothermal synthesis are crystal nucleation and crystal growth. And this is what we see in this slide. If we look on the left side, we see the transfer of convective mass of the species that make up the precursor solution to regions where the species combine in a stoichiometric ratio, starting the nucleation of small crystals here named ABC. If we look on the right side, now we see mass transfer of dissolved species to the surface of existing crystals, promoting their growth. Here, okay, here we see the growth mechanisms. The growth occurs by oriented aggregation, which is shown here, when small particles with high surface energy aggregate in an oriented way, forming large particles to reduce their surface energy. The system also changes to a lower energy condition by dissolving smaller particles and anchoring the released ions on the surface of larger particles in a mechanism known as Ostwald ripening. Here we summarize some of the advantages and disadvantages not only of the solvothermal method, but comparing to other synthesis methods of ceramic powders, such as the solid-state reaction, co-precipitation, sol-gel method, and polymeric precursors. So we see that considering the cost of production, we can consider it as a moderate cost. And this is a scale based on the comparison of the other methods. The composition control is either good or excellent. The morphology control is very good. I don't agree with good here, but I follow the classification brought by this author. I think morphology control is very good, and we can prove it later on with the slides that will be shown here. Powder reactivity is good. We can achieve powders, nano and submicro powders with more than 99.5% purity. There's no calcination required and also no milling. And these are the main advantages of this method. Let's talk about some process parameters, starting with the precursors. So the precursors, they should allow adequate solubility for the release of ions, the ions that be used in the formation of the target material, and also used in the stoichiometric way. As for the solvents, the chemical potential of ions dispersed in a solvent is inversely proportional to the dielectric constant of that medium. This relationship affects the solubility of precursors or intermediate compounds formed in the synthesis. For water, which you see here in this graphic, the increase in temperature results in a decrease in its dielectric constant. Below the supercritical water temperature, which is around 374 degrees Celsius, the electric constant does not show a significant dependence on pressure. However, above this temperature, the dielectric constant drops sharply as the pressure drops sharply at low pressures, around 230 bars, and decreases mostly at high pressures, 1 kilobar. As for the solvents, solvents are another factor that must be considered in the effect of solvothermal conditions on solvent viscosity. For water, the viscosity decreases with increasing temperature, which favors diffusive processes. The temperature is a critical parameter because it determines the chemical kinetics and therefore the morphology, the chemical composition, the crystal structure, and also affects solubility and reagent decomposition. Now for the pressure, the solvent has the function of conducting the thermal energy and also to increase the pressure during the process. Each fluid, each solvent has its own relationship between temperature and pressure, as we see here in this picture. Pressure has no significant effect on crystal growth rate, but it influences other parameters such as mass transfer and solubility and therefore morphology. It is possible to vary the autogenous pressure, which is the inherent pressure of the process, just by varying the filling percentage of the reactor volume, or we can apply an external pressure, which is what we do in our reactor. So as I just mentioned, we can use additional pressure using a gas, the injection of gas such as argon, nitrogen, methane. And this is also another process parameter that we can use to tailor the characteristics and the properties of the resulting powders. So the pressure induced effects are stabilization of denser structures, higher thermal stability of the reagents, higher chemical reactivity, and also higher reaction kinetics. We can also use mineralized because many compounds do not solubilize just by being added to a given solvent under certain conditions of temperature and pressure. In this case, mineralizers are substances capable of providing solubilization. Also, they are used to adjust the pH of the solution. These are the main mineralized used in solvothermal synthesis. And we also make use of surfactants. They help control nucleation, phase homogeneity, size, morphology, and dispersion during crystal formation. They are usually amphiphilic fatty acids. That is, they have a hydrophilic and a hydrophobic constituents. Examples are sulfated esters or sulfates of fatty acids, anionics, and quaternary ammonium salts. So they also help when complex morphologies are needed to be achieved. Okay, so what I'm going to show you in this work is not only the results of powders, the synthesis of barium titanate powder, but also the design of a reactor, which was part of a PhD thesis by one of my former students and today colleague, Armando Monte. So some aspects have to be taken in consideration when a reactor is designed, which is the easy of assembly and disassembly. It's not useful when you have a piece of equipment at the lab that it's hard to assemble, disassemble, to put them out, to change samples. No? So the heat exchange and the pressure resistance. So this determines the kind of material you use. Sealing, of course, no? As we are using pressure. So the system has to be sealed, and also the corrosion resistance of the constituent materials. Okay, we are now divided into two classes of ceramics. We start by oxide ceramics, which is the example I'm going to give today. But the method, the solvothermal synthesis, can also be used to produce non-oxide ceramics. Oxide ceramics are easy to obtain because oxygen-rich mediums are easier to control. The formation energies are relatively low, especially compared to non-oxide ceramics. The crystalline powders produced at temperatures are much lower than those of the solid state reaction, which is one of the main advantages of this method. So the formation, the temperature formation of some of oxide ceramics, they may range between 100 and 200 degrees, which is very different from those obtained from solid state reaction. And also we can use Teflon liners. I'm going to show you schematics of the reactor in a few minutes. So we can use Teflon liners to prevent contact of the corrosive reaction medium with the reactor wall resistance, which is much easier than other materials now that metallic materials that we can use to control to prevent corrosion. Non-oxides, they have strong bonding, covalent bonding, so they are not as easy to produce because they also require high energy formation, higher temperatures, special synthesis conditions to avoid oxidation reactions, inert atmosphere, oxygen-free solvents, and they, as I mentioned, they required higher formation temperatures above 300 degrees Celsius, and therefore higher autogenous pressures and higher applied pressure, external pressures when needed. Also, special construction designs such as resistance to higher temperatures, higher pressures, and corrosion. So in this case, we may not use Teflon liners. We have to use quartz liners, which increases the cost of the reactions. Okay, so this is the original work, the original PhD thesis by Armando Monte Mendes. He's now a postdoc here at our group and continues to use the reactor he designed, which is shown in this picture here. Here we have an example of a solution being put in a Teflon liner and inside the reactor where the synthesis will take place. This is the schematics of the whole system. Here we have a magnetic exterior and electrical resistance to heat the reactor, an autoclave to apply pressure, a thermocouple to control temperature, a pressure transducer. Here's just a siphon and a valve. The gas line that connects to the cylinder, which in our case was argon, and a computer to control the synthesis. We can, in fact, do this from home now because some synthesis take long times. So we can do it. We can just view, monitor the system remotely. Okay, so the beginning. As pressure has a direct effect on the characteristic of the material formed, we chose to test the reactor and test the synthesis conditions in this new equipment using a well-known material. So for this reason, we chose barium titanate. We have vast literature on the synthesis of barium titanate, so we could actually compare our results with those produced by other authors. And also, it's not just any material, because barium titanate powders, they have electrical and optical properties which are very useful. And this is literally the first work produced under pressure, because Armando was about to defend his PhD, and he had to publish a paper. But it took a long time for him to produce, to actually build the reactor. So this is the first work that was produced using this equipment. So the pilot synthesis aimed at verifying the effect of pressure on the solvothermal synthesis of barium titanate, under the assumption that the pressure affects the solubility and the chemical kinetics, the reaction kinetics, and therefore we might expect changes in composition, we might expect changes in morphology. So the specific objectives of the work was to design and construction and build a solvothermal synthesis reactor adapted for gas injection, the development of a suitable synthesis route to assure reproduction in the case of barium titanate, to map the temperature and time progress of the morphology and composition, and to apply external pressure to investigate high pressure synthesis by the injection of ultra pure compressed argon. So we chose barium titanate. It's a well-known material. It has a perovskite type structure with ferroelectricity and piezoelectricity properties. Actually, the lead titanate has better properties, but from the beginning of the 21st century, they have, following European guidelines, lead cannot be used anymore. So this drive the research on alternatives to lead titanate, and barium titanate is the most important one. So the electrical properties of barium titanates allow its use, for example, in capacitors. But if you choose the solid state reaction route, which takes place above 1000 degrees C, it doesn't help much in the control of the particle size. And if we talk about microcapacitors or nanocapacitors, we are talking about 2 and 3 micron thick layers of barium titanate. This is one of the applications of the solvothermal route. So using this route, we can produce barium titanate powders by low processing temperatures. We will see what we call low, and also unlikely to form other phases, such as barium carbonate, which is not good for the control of the electrical properties, especially for nanometric components. And this is very nice. We can actually vary the morphology of the powders by controlling the process parameters. So this is the reaction involved in the production of barium titanate. The precursors that we can use oxides, chlorides, hydroxides, nitrates, alkoxides. We chose one route, and we can use a solvent water plus alcohol, just alcohol, and mineralized. We can use potassium oxide or sodium, potassium hydroxide or sodium hydroxide. So these are the starting materials that we used in the synthesis I'm going to show you. So we use nitrate, barium nitrate, we use titanium isopropoxide, TTIP, and as mineralized, we use potassium hydroxide. As solvent, we use water plus alcohol. And the mineralized solution was one molar solution of potassium hydroxide. So we start by two solutions, a solution with the TTIP, which is the titanium precursor, one solution of the mineralized. The solutions are mixed, slowly dripped to precipitate hydrous oxides under cold magnetic stirring. The pH is adjusted to 14 because here we have high solubility, and under these conditions we apply pressure. So to apply external pressure, we used extra pure argon. The lowest synthesis conditions we investigated were from 80 to 100 degrees C, from times varying from 15 minutes to 1 hour. So we also mapped the 120 to 180 degrees C temperature range, times ranging from 6 hours to 24 hours, and high pressures at 180 degrees C. The pressures vary from 20 to 80 bar. So this is the rinsing protocol. What we see here is a sequence, is a series, of rinsing, extracting the liquid aliquots, and then centrifuging, ultrasound and centrifuging, until we achieve this. This is the optimized route after several tests, which allows us to achieve so high purity of the synthesized powder. So it's a sequence of 5 rinsing sequences. This is our rinsing protocol. And then the powder is kept in an oven at 60 degrees for 12 hours for the final drying. Characterization of the powders took place by XRD, field emission scanning electron microscopy, and BET surface area. Here we see a pressure profile. What we see as the temperature increases, we see an increase in pressure. This is the inherent pressure or the autogenous pressure of the reactor. So pressure increases because the temperature increased. This is normal. And we also applied external pressure to adjust the pressure to the levels I mentioned before, from 20 to 80 bar. Okay. So in general, all samples synthesized between 120 degrees and 180 degrees for 6 to 24 hours presented only the barium titanate phase, tetragonal phase of barium titanate, and free from any secondary phases, deleterious phases such as barium carbonate. All the samples synthesized under high pressure also showed single-phase stabilization of barium titanate, free from contamination, and just as samples synthesized between 120 and 180 under inherent pressure, they showed the tetragonal phase. These are the lowest temperatures used. 80 degrees Celsius, we couldn't see the formation of barium titanate. 110, we see just the start of crystallization of the phase. But it's interesting to see that when we move from we go from 110 to 120 degrees, just 10 degrees, now the same time, then we see the formation of barium titanate, and we don't see any other crystalline phase. Of course, here we don't have 100% crystallinity, as I'm going to show you in the pictures, but we see single phase formation during the whole temperature and time range investigated. So mapping the temperature versus time, starting at 6 hours, 100 degrees, the temperature was fixed at 100 degrees, 6 hours, same pressure, just to see the effect of the increasing time for the same temperature. We see very, very small shift of the main peak of barium titanate, but we don't see the formation of any other phase. Here, we maintain the temperature at 180, but now we increase the pressure to see the effect of pressure. Actually, here on the top, we have the inherent pressure of 10.3 bar, 20 bar, 50 bar, and 80 bar. And we see that, as we expected, the increasing pressure does not change the composition, does not change the phase formation, just the characteristics of the particles. Now we're going to begin a series of micrographs to show the effects of temperature, time, and pressure on the powders that we obtained. So we started 80 degrees C, 24 hours. The pressure is autogenous pressure. What we see here are rough spheres of rough appearance of amorphous hydrous oxides, as confirmed by by the XRD results, we couldn't see the formation of crystalline barium titanate. 120 degrees C is 15 minutes autogenous pressure. Then we see the onset of crystallization from the amorphous phase in solution and self-assembly of the first mesocrystals, as shown here in this arrow. So here we have the amorphous phase, and here we have the first mesocrystals. Increasing the time from 15 minutes to 6 hours. We didn't change the pressure. Now we start to see some nanoparticles of cubic geometry still dispersed in an amorphous phase of average size 85 nanometers. Increasing to 12 hours, we see here now the solubilization precipitation oriented aggregation of the powders. This is one of the growth mechanisms we're going to discuss in a few minutes. 18 hours, we see the increasing mesocrystals. It's nice when you can actually, it's not possible to do it here. We should have done as a movie, no, as a film. It's very nice when you see the time increasing for the same temperature and then the temperature increase and you see the change in the morphology and size of the crystals that are formed. Here we are at 24 hours. We still have organic material, we still have amorphous phase, but the content of mesocrystals now is much higher. At 140 degrees C, 6 hours, autogenous pressures, we have a 1-to-1 ratio between mesocrystals and smooth irregular particles and low amorphous contents because we are at higher temperatures. So the kinetics here of the formation, here we have a very nice sequence of mesocrystals shown to you. And this scale here is 200 nanometers. 140 degrees, 12 hours, autogenous pressures. Now we have the growth of irregular particles at the expense of the former mesocrystals, and a subtle increase in particle size. And the amorphous, the content of amorphous phase now is vertically zero, is virtually null. 140 degrees is 18 hours autogenous pressure. We continue with the growth of the particles following the mechanism of oriented aggregation, as it can be seen here on this neck formation here in this picture. I always have to thank Armando for his patience, not only to build the reactor, to synthesize the powder, but to obtain this, in my opinion, these very nice pictures that show the sequence of events with temperature and time. This is a real mapping. This is a real temperature and time mapping. And pressure, as we see in the next micrographs. So 100 degrees C is 24 hours autogenous pressures. We now have lower contents of mesocrystal, higher contents of smooth irregular particles, increase of particle thickness, and we don't have an amorphous phase anymore. So we can, from these pictures, realize that the two mechanisms that take place here can be seen in the pictures. Here are the different temperatures. So let's take, for example, 140 degrees C. What we see as time goes on, we see oriented aggregation, as shown in the picture before. With oriented aggregation, because of this disordered area here, we see a slightly reduction in the size of the crystallite, which is opposite from what we see at 180 degrees C, for instance, where we see particles growing from Ostwald ripening without the disordered area between them. And then in this case, we see an increase in the crystallite size. 160 degrees, 6 hours, the system goes on. Particle size is around the same as that we saw before at 140 degrees for 6 hours. 12 hours now, predominance of irregular particles, low and constant contents of mesocrystals, and the growth mechanisms. The most relevant growth mechanism here is Ostwald ripening that drives the particle growth. 18 hours, same temperature, 160, 18 hours. Again, predominance of irregular particles, significant growth rate because of the increase in temperature. 24 hours because of the increase in time. 24 hours, we have now about around twice the size that we had at 6 hours. So it took from 6 to 24 hours to double the size of particles. Now we increase the temperature to 180 and begin from the lowest time, 6 hours. We see the highest growth rate so far because the temperature increased. So we, even at low times, we have the predominance of irregular particles, and the contents of mesocrystal is lower than that of we observed at 160 degrees. At 12 hours, high growth rate, and we see the particles growing again. 18 hours. Now we see something interesting, which is showing this arrow here, the start of the formation of dendrites, which is a morphology we haven't seen before. 24 hours, again, Ostwald ripening, high growth rate. Now we have 3 times the size that was observed at 140 for 6 hours. And now we begin with pressure. Now let's see the effect of pressure. We saw from the X-ray diffraction that pressure does not affect the composition, does not affect phase formation, but affects morphology. So when we increase the pressure to 20 bar, 180 degrees C, 18 hours, 20 bar, what we see is the dendritic morphology. And we continue observing the oriented aggregation, but now the compacted oriented aggregation imposed by the external pressure. 20 pressure particles are therefore compact aggregates and start to show the flower type morphology. 50 bar, increased dendritic, wow, that was tough. Increased dendritic morphology, and we will see what comes from the flower type morphology that we saw before. No apparent growth from 20 bar, just the change in morphology. Now again, the flower type morphology, and the particles are increasing in size from compact aggregates. Now 80 bar, and the powder is totally different, completely different from the powders that we obtain at lower pressures. So we see here the flowers, and we could actually measure the main branches and the ratio between the main and the secondary branches of the flowers. And we saw that the main branches are about 3.5 microns long, and the ratio between the main and secondary branches are about 4.7 times. Here are the secondary branches. We could measure the angle between them, and this is a close-up of this morphology. 80 bar, we see both 2D, 2 dimensions, and 3-dimensional dendritic morphology, both from the flower type morphology that can be explained from where the particles start to grow. If they start to grow from rod-like particles, if in the beginning of the nucleation growth we obtain rod-like particles, then they grow in the 2D geometry. But if in the beginning of nucleation we got spherical particles, then the spherical particles grow and achieve a 3D flower type geometry. And these results can be seen in the work by Young, which you can just take a picture of this code, and we will drive you directly to this work. Also, another work by Tong, 2012, showed the self-assembly of by Ostwald ripening, resulting in the 3D geometry of flower type particles. So the injection of argon, inducing the increase in pressure, worked with the solubilization of the gas in solution, and this increases the difficulty in mass transportation from ions to crystal, and increase the kinetic potential of the reaction, improving crystal growth, which drives the formation of dendrites. So again, here is the flower type morphology. This schematics here shows the formation of the flowers from Ostwald ripening of dendrites. So the dendrites that we saw in the beginning of particle growth, they result in flower type particles. And this work is by Xu, 2011. Here's a summary. This work also was done by Armando. It's published in his paper. So here we have two y-axis, one with the temperature, one of the pressure, and here we have time. And it's very nice to see that what changes when we increase either time at the same temperature and pressure, or we increase pressure with the same time and increasing temperature. So this is the full mapping of his work. And we when we go to the highest pressure, higher than 10.5 bar, which is the highest inherent pressure the system provided, then we see here we see the beginning of dendrites, but flower type 2D and 3D flower type morphology we only see at the highest pressures. And here, this top picture here is the original amorphous morphology. So to conclude, so this work showed the construction of a synthesis reactor that allowed the application of external pressure. The reactor performed very, very nicely and still does these days. So we investigated solvothermal synthesis processing at different temperatures, time, and pressures applied to barium titanate. We could see the change in the thermodynamic behavior of the system with external pressure resulting in different morphologies, but the period of the phase was maintained. Stabilization of pseudo-cubic and tetragonal phase. The tetragonal phase was the phase that we most observed. The peak shift that I showed you was characteristic of this early pseudo-cubic phases formed. The morphological evolution of particles and growth mechanism was explained as a function of temperature, time, and pressure, and we could obtain complex morphological changes such as dendrites glowing into flowers in 2D and 3D under high pressure without the use of any special additives to result in these morphologies. I think this is it. I thank you very much for your patience, for your attention, and for the opportunity of showing some of the work that this synthesis group performs here at UFRN. Thank you very much. I'm at your disposal.
Thank you.
Thank you.
Professor Martinelli, for this brilliant presentation, and also for the opportunity to show to our students this interesting technique and results. So we are opening this section to questions. We have some questions here. First of all, Professor Martinelli, despite the importance of pressure, temperature, and timing as relevant parameters of synthesis, is there some other way to control particle sizes, morphology, or orientation, considering any specific material synthesized using the solvothermal technique?
You can use additives, but the question is what for? Because anytime you use an additive, you change the whole process, you know. So if you can use, if you can achieve the same results using the least amount of additives, it's even better. But you see, I don't have a pressure reactor. Okay, if you don't have a pressure reactor and you require a different morphology, then you have to study additives for that. If you go to the literature, not for all materials, this is another point. It will also depend on the material that you want to synthesize. There are materials that you have vast literature on that. So the point is, how if you have a pressurized reactor, what can you do? You can investigate the effect of pressure. But if you don't have a reactor, you have to select additives. The question is, what additives? So the same additives result in the same effect for different materials? Perhaps not. No. So this is something that you require literature to drive your work. And if you have the opportunity of changing the pressure, perhaps you don't require as much literature. You just go to your equipment, you increase the pressure, which is what we did. You go to the equipment, you increase the pressure, and then you see the kind of effect that you have. And I know for the first time we see the presentation, Professor Edgar, we assume that they were all surprised at the morphology. But this is not a surprise. Once you start to investigate why, you start to ask why those morphologies were observed, then and you know the mechanisms, then you can by yourself start to imagine what kind of mechanism my material will show once I start to increase the pressure. So there are other ways, as the question implies. Sure, there are other ways. There are chemical ways. This is not the only synthesis route. There are many synthesis routes, which is something that you have to consider before you want to synthesize your material. If you don't have another opportunity, it's tough. But if you have, think of yourself as a company that wants some kind of material. Why is this company focused on one synthesis route if it can choose from different synthesis routes? So the synthesis route itself is a parameter that you have to choose before you start to make your material, to produce your material.
Okay, very interesting. So there is a lot of chemistry behind the importance of additives and the reaction.
There is a lot of chemistry. It's not easy. I showed you, one of the other. I think I can. Do you think I should continue sharing the presentation, or I can start now? I can stop now. Oh, I'll just leave like this. No. So we have collaboration from a company which is ArcelorMittal, which is one of the major steel making companies in the world. We have an ongoing project to produce titanium boride particles, non-oxide, different system. And we are still trying to do this by around 2 years now. So we don't have full control of the chemistry and of the process parameters of titanium diboride. Now, so what we can do? I just mentioned this, Professor Edgar, because you said there is a lot of chemistry involved in the system. Yes, and that's why we chose barium titanate, because you have a lot of literature. Most of the chemistry of the system is known. If we start from a system where the chemistry is not well known, and you are limited to the parameters of your equipment, then it's not always easy to produce what you want. We are trying for 2 years to produce titanium diboride. We achieved titanium oxide, and we are now trying to to exchange ions to see if we can induce the inclusion of boron ions in the system. Then with another treatment in the same reactor, then we reduce and eliminate oxygen. So it's a lot of chemistry in each material. You're right.
Okay.
Well, I'm a physicist, but I have to admit that the chemistry of materials is perhaps as important. I'm not humble enough to say that it's more important than the physics of materials, but it's as important as.
Okay. Any more question? Camila?
Professor Martinelli, it's always a pleasure to hear from you.
Hi, Camila. Always a pleasure to hear from you.
I was wondering, when you talked about you take a perovskite and try to make different inclusions of different elements. Well, our group also is interested in perovskites. They're really an interesting type of kind of a structure. And recently we're exploring the high entropy perovskites. And I was just wondering how, if you, since you have a group of diverse researchers and you have much connections, if you were also wondering of the applications of morphology using this kind of high entropy perovskites.
No, we investigated titanium. I just missed myself here. We just investigated this material because we have literature on that, But we are now interested in the synthesis of non-oxide ceramics. But I would be very, very interested in exchanging information with you, Camila. Perhaps we could do a collaboration together. We have the equipment, you have knowledge. Who knows? Perhaps together we can achieve this non-oxide ceramics. We
That would
haven't
be
moved
really
for.
amazing. Sorry.
Okay. No. Okay. Well.
No, please go on. Please go on.
Yeah, perhaps we have moved to non-oxide ceramics fast because of this collaboration with industry, Camila. But we are very interested in hearing, exchanging information. Perhaps together we can achieve this structure. This is our main objective by now.
That would be awesome, because the route we use, it's high energy vibrational milling or mechanical alloying. So we do not explore the morphology just as your group does. Mm-hmm. And as we saw in your presentation, the morphology can really exchange the applications in some ways. We do not did not see just the nanometric powder.
It works the other way around, Camila. You are very, very welcome to try some tests here. If we can come here, it would be a pleasure. Otherwise, we can arrange some sort of collaboration using cameras and internet and prepare some solutions and powders for you here. Collaboration works both ways.
Awesome. Thank you very much. You're always too kind to us. Thank you very much.
Come on.
Thank you, Camila. Any more questions? Professor Martinelli, and what's happening in this scenario about Solvothermal? What is new in this area? What the researchers are doing relating to new discovery and new materials?
What we see here is basically oxide ceramics and changing, especially controlling morphology and controlling particle size because of the increase in the nanometric devices. The need of producing smaller powders that do not aggregate, that you don't require calcination, you don't require milling. So I think, Professor Edgar, these are the main advantages, and that's why this technique is being studied, and also the effect of different solvents. There are many process parameters that have to be investigated for different powders, and if you increase pressure as one of the process parameters, which is nice because as I showed you, for this case, I don't know if it's a general conclusion. I'm always afraid to say always. I'm always afraid to say never. No, but I don't know if it's a general conclusion. But from what we see, the increasing pressure does not change the composition, which means you have a technique, you have a route that provides pure powders, and you have another process parameter that does not change the purity, even if you talk about change in the phase formation, because barium titanate has different phases, and we didn't see a change in phase, and we explored a very considerable pressure range from 10 to 80 bar. So it's not the whole range, but it's a considerable range. If you want to move to a different range than that, I don't know. But I don't see many different conclusions in that. So what I see from this technique is the possibility of varying different parameters. It's different than polymeric precursors. It's different from sol gel. So we have many parameters, and you have the possibility of controlling important characteristics of the powders. Especially if you talk about nanometrics and submicrometric powders, you can control these characteristics, changing the solvent, changing the pressure, and you can make a tailored combination of parameters for each different material. It's easy to come here and in a few minutes, in 45 minutes, 50 minutes, show you a considerable number of micrographs. It's not because it's one of our works. As I'm saying, I'm always grateful to Armando because of his patience. We have a large number of micrographs investigating each of the parameters: time, temperature, pressure, and the combination of that. This map that I showed in the beginning, in my opinion, and it's not mine, it's Armando, so I can say it's very, very comfortable. This is a treasure, Professor Edgar. Let me just show you again. If you ask me, choose just one slide. I want to give you 1 minute to present this paper. Choose one slide. I would choose this one, because this slide show you the morphology characteristic of a considerable number of powders. And to obtain this, then it's extensive lab work and it's extensive microscope work. And if you say, but what about the composition? Then I can answer in one phrase. All the powders have the same composition.
The same composition.
I think this is the treasure of this work, and it's the treasure of this technique. Of course, if you invite another speaker to talk about other techniques, he will show you the advantages of solid-state route, the advantages of Sol-Gel. Of course, all techniques have their advantages, and this is the main advantage of this one.
Fantastic, Professor. Thank you, Professor Martinelli. Thank you so much. Temos mais uma pergunta, Camila. O Chula também quer falar, né?
Não, eu só queria falar, a gente pode abrir o vídeo para tirar uma foto, para registrar.
Ok. Please, Edgar.
Camila, desculpa.
Me manda essa foto, se tiver. Adoro. Adoro.
Camila, você queria falar alguma coisa? Acho que eu ia interromper.
Sim, na verdade aqui abriu espaço para mais tempo, né? Mais perguntas. A pergunta seria, professor Martinelli, se a partir de... O senhor conhece as rotas que a gente utiliza aqui, né? Por meio de moagem mecânica. Então, o que eu obtenho é um pó muito fino. Às vezes eu tenho tamanhos de cristalitos similares, né? Mas às vezes eu obtenho uma coisa bem mais caótica do que num Sol-Gel. Então, a pergunta é se seria possível integrar essas técnicas, né? Eu consegui uma cerâmica através de moagem mecânica de alta energia e iria tentar trabalhar a morfologia dela a partir dessa amostra moída.
Acho que não, porque a gente começa a trabalhar a morfologia na síntese.
Sim, era essa a minha pergunta.
Não. Mas assim, a gente pode fazer com precursores. É um trabalho de colaboração. Eu ficarei muito feliz de trabalhar em colaboração com você, com o grupo daí. Eu adoro vocês não têm noção quantos amigos eu vejo aqui. O Frota, o Bocão, o Yuri e muitos que não estão aqui. O Darbens, muitos, né? Eu adoro vocês. Tem gente pessoas formadas aqui, que são professores, aí eu adoro vocês. Então, ter um trabalho em colaboração com vocês seria maravilhoso. Eu acho a rota de mecanossíntese, Camila, ela é legal, né? Mas ela tem algumas limitações. Quando você falou caótico, pronto, tá aí a limitação. Você não tem aquele controle. Aqui você controla a morfologia, você controla o crescimento, você controla o tamanho de cristalito. Foi muito rápido, né? Mas eu te mostrei que por agregação orientada ou por Oswald Ripening, né? Você sabe se o cristalito vai crescer, se o cristalito vai diminuir ou vai se manter. Então, o que você faz? Você privilegia o parâmetro, temperatura, tempo, pressão, para quê? Para que você governe a rota de crescimento. Você tem controle sobre isso, você tem muito controle. Agora, não dá para dizer assim, como que isso se aplicará a um outro pó cerâmico? A gente não consegue fazer isso. Por quê? Porque, como o professor Edgar falou, é muita química. Então, você precisa conhecer os precursores, saber que solução que vai ser formada, como que vai crescer aquela primeira fase, né? Os primeiros núcleos, né? Como que isso vai nuclear? Mas é possível a gente fazer. Precisa de gente, né? Que bom que precisa de gente. Porque num mundo onde a gente precisa cada vez menos de gente, tá ficando um mundo muito chato. A gente precisa de gente. Então, se tiver
colaboração.
De colaboração. Se tiver um aluno de mestrado, de doutorado, eu vou fazer por mecanossíntese, posso fazer para comparar por síntese solvotérmica? Claro que pode. Pode fazer. Pode vir para cá. Ou melhor ainda, eu levo o reator para aí. A gente faz aí na casa do Bocão.
Sim. Sim, parece bem mais divertido.
Martinelli,
o senhor vem comer um tambaqui aqui.
Desculpa, fui citado. Não brinca que eu já fiz partícula de ouro botando um balão dentro de uma caneca no forno de micro-ondas, tá?
A chave de onde está o reator. Foi o Armando que fez, mas é do patrimônio da UFRN. Eu vou lá, pego o reator, boto embaixo do braço e levo. Aí tem gás, não tem? O reator é pequenininho, é isso aqui. O resto vocês têm aí. É fácil de fazer.
E como
Super.
o professor Marcos diz, ainda tem geladeira, não, professor Marcos?
Vocês querem algum extrato de planta? Eu tenho um monte de folhas que veio aí do Rio Grande do Norte, uma colaboração.
Eu tenho um recurso para executar aí.
Pronto, era o que tava faltando dinheiro. Agora que tem
celulose aí na geladeira, tem um monte de coisa.
Os amidos, a gente está fazendo trabalhos tão bonitos com amidos, com o professor Pedro, com o pessoal da Unicamp.
Que legal. A gente está fazendo grafeno aqui no reator. Grafeno.
Nossa.
Mas grafeno já se faz aí fora. Sob pressão eu não vi. Tá saindo coisa boa.
Rotas diferentes, né? Isso é muito legal, professor. Muito empolgante. Eu acho que cada palestra sua nos dá um ânimo.
Que legal.
Novas
feliz.
Ideias.
E não é da boca para fora, não, porque a gente está aqui. Estamos aqui para colaborar, Camila. Você tem meu e-mail, WhatsApp, a Edgar também tem, Bocão, Sérgio. Podem entrar em contato, a gente fecha a colaboração na hora.
Ótimo, estou empolgada com isso.
Tá bom.
Obrigada, professor.
Eu que agradeço.
Obrigada também.
Muito obrigado.
Obrigada a todos.
Muito obrigado. Cadê a foto, Edgar?
O professor Anchula fez um print já ou não?
Eu já fiz, depois eu mando para vocês.
Manda, por favor. Manda que eu guardo.
Agora que apareceu ele, Miller.
Agora eu vou tirar mais pessoas apareceram.
Olha o Yuri aí.
Todo mundo olha para mim agora.
Para a câmera, por favor.
Ótimo. Obrigado.
Opa.
Obrigada a vocês.
Só lembrando, pessoal, que agora às 2h nós vamos ter a palestra da professora Virgínia, lá do México. Então, daqui a pouco, esperamos todos de volta aqui para o evento, tá bom? Professor, muito obrigado.
Obrigado a vocês mais uma vez, Edgar. Um prazer.
Numa próxima oportunidade.
Obrigado. Até logo.